In the final application of flow that I'll be going over, we're going to consider the project selection problem. In the project selection problem, you are given some set of projects, and each project will have a positive reward or some negative reward, i.e., each project has some profit or cost. Some or all projects will have dependencies, i.e., other projects that must be done in order to do this project. These dependencies could be cyclic, and these dependencies represent the fact that if you do some project U, if you pick your set of projects such that it contains the project U, a dependency of U depending on V means that the project V must also be in your set. And so you can only pick project sets that every dependency is properly accounted for. This also means that the empty set of projects is always a valid answer. Your goal is to compute what the reward or the maximum reward you could get by picking some valid set of objects or a set of projects. You can't just pick all positive projects, because by picking all the positive projects, it is possible through their dependencies that they might depend on a large summation of negative projects or negative reward projects that would lead to an inoptimal reward for your given set. And so the project selection problem is to pick some set of projects and determine what the maximal weight set of projects you could pick that maximizes this reward. Our solution using flow will be to create a node for each project. And we will connect the source to all projects that have a positive reward. And the connection will be with capacity equal to that positive reward. We will connect all projects with a negative reward to the sink. And the capacity on the edge will be the absolute value or the negation of that negative reward. For any project U that depends on project V, we will add an edge in our graph with infinite capacity from U to V. Notice that this graph may not be bipartite, because positive reward projects could depend on other projects with a positive reward, and so could negative reward projects, which would break our bipartiteness property if we were trying to split into two groups, if there were enough dependencies to break this property. We claim that the answer is the sum of all positive reward projects minus the flow of this graph. If we consider the graph induced by some project set that has projects with a positive reward of 4, 6, 2, and 3, and projects with a negative reward of -2, -3, -5, and -8, and a small list of dependencies, which notice that for two of the dependencies, they are between projects that both have positive rewards. This graph is not bipartite. We claim that the answer will be the sum of all the positive reward projects, so 4 plus 6 plus 2 plus 3, minus the flow, i.e. the minimum cut of this graph. The reason why this is because we can only cut the edges from the source to some of our positive projects, or from our negative projects to the sink. Any of the dependency edges we can't cut because cutting them would imply an infinite cost, which we want to avoid. We can see that cutting an edge from the source to a positive project is actually representative of excluding that project from some set S. And cutting an edge from the negative nodes to our sink actually represents including the project in our set S. And the reason why this represents including the project is because we have to remember that the capacity of these edges are actually the negation of the project costs. And so cutting the edge is equivalent to adding the negative cost to our set S. And so it is clear that the set S will have some minimum costs for what it represents, but we also have to see that the set S that this induces will be valid in regards to our project selection criteria. And the reason why it will be valid is because there only exists a path from source to sink if there is some positive project that we've selected, and when we trace all of the dependencies, there is no path to the sink. Because if there were a path to the sink, that would imply that there is some project that we haven't included. There is some project that we are including for the positive projects that may rely on certain other positive projects. These positive projects could also rely on negative projects that rely on other negative projects. And eventually we get down the line where we have a negative project that we have not cut, i.e. we have not cut this edge. And since cutting this edge represents including a project, that means that this edge existing, us having a path to the sink, actually represents this project not being in our set. And so since we are trying to minimize our weight of the set, we will successfully minimize it, but also in our min cut, it will represent a valid set that does not break our project selection criteria. And so what we can see is that we claim that the answer, the total answer to our problem, will be the sum of all positive projects minus the weight of this minimum cut. And the reason why this is the case is because the minimum cut represents some set S of projects where we have the sum of positive projects that have been excluded from this set S plus the absolute value of the sum of negative projects that have been included in this set S. This is also equivalent to subtracting the sum of the negative projects included. Notice that this is kind of like a double negative. This is maximal because we can see that since the sum of all positive projects is fixed, we are essentially minimizing the amount that we subtract from all the positive projects we take. We can see that the sum of all positive projects minus our minimum cut, we can actually rearrange this section right here, which is the sum of all positive projects minus the sum of positive projects excluded, to be rewritten as the sum of positive projects included. And since right here, since this whole section is doubly negated, right, we can distribute this negative over, and we can see that this also comes down and becomes the sum of negative projects included. And therefore, these two are actually equivalent. And this is clearly the weight of our project set. And since the minimum cut will only induce a valid project set, and we make the claim that by subtracting the minimum cut, which is minimized, from this set of all positive projects that we are actually maximizing this whole statement, and that this statement is exactly equal to this statement, which is very clearly the sum of our selected projects, we can see that taking the sum of all positive projects minus the weight of our minimum cut from our graph, which induces a valid set of projects S, will give us our maximizing answer.